Hello everyone. So in today's class, we will learn dimensional analysis of some physical quantities. I will explain you one more time how to find dimensions of some physical quantities which are a little bit difficult. So let's start. So how many of you understand dimensional analysis definition first of all? So yesterday I told it is what representation of one physical quantity in terms of powers of basic physical quantities. So shall we take one general example? Okay. So see here, I am telling you one general example of this dimensional analysis. Okay. Now see here, this is a farmer. Okay. Who is this? A farmer. And now he has to give, let us suppose, 10,000 rupees. 10,000 rupees he has to give. Okay. How many rupees he has to give? 10,000. Right. But he don't have money. But he don't have money. Then how to give this 10,000 rupees? Okay. But what he has two goats, okay, and one hen, okay, and let us suppose one dog, right? Now each goat price is 4,000 rupees, and this hen is of 1,000 rupees. Important hen this is, okay, right? And dog is also, let us assume that its price is also 1,000 rupees. Now he has to give this 10,000 rupees, but he don't have this 10,000 rupees. So what he is doing now? What he will do? What is the option? What is the option? See here. This farmer yes or not? To compensate this 10,000 rupees, okay, what he will do? Two goats he will give plus what? One hen and one hen and one dog. How much it is? Okay, not 10,000. This is 4,000 into 2, right? Okay, plus here it is 1,000 into 1, plus this is again 1,000 into 1. Okay, na 10,000. Yes, 4,000 into 2. So what you understood from this? See, representation of this 10,000, I can do like this. Yes or not? Right? I have represented this 10,000 rupees in terms of this story. Okay. Similarly, this is what basic things which he has, right? And he has to compensate this 10,000 rupees. So that's why he has given that all or represented like that. Take this instead of that. Similarly, when we are having one physical quantity, that is force, how we are representing in terms of mass, length, and time. 1 in mass, 1 in length, minus 2 in time. So what is this dimension analysis? What you understood from this story and all? This story you leave it now. Okay, this is just for understanding. But what you understood now from this? We understood that this dimensional analysis, already I told, yes, dimensional analysis is nothing but, what is this? Representation of any physical quantity in terms of powers of basic physical quantities. है ना? That's what this dimensional analysis is. Don't write this part, just this is for understanding. Okay, so let's erase this and let's move ahead now. Okay, so this is what dimensional analysis. So already in yesterday's class I have explained how to represent this dimensional analysis, means particularly the basic fundamental things. For example, mass represented by m, length represented by l, time represented by t, and so on. Yes, yesterday I have given one table. So let's see in today's class some dimensions of some physical quantities. Okay. So already yesterday I have told you that you please make that table. Okay. So let's see today. Dimensions of some physical quantities. Dimensions of some physical quantities. So let's take little bit difficult one, right? So some simple, I felt that you might have done. So let's see this resistance. Dimensions of resistance. Resistance is R, you know, in 10th class you have learned. Okay, resistance means what? Opposition to the current flow, resistance R. Okay. Now see here. This is resistance R. Now, we know Ohm's law, hai na? Yes. So when you are finding the resistance or any dimensions of any quantity which is given, first try to get the formula. Okay. So resistance in which formula it is coming? It is coming in Ohm's law. So we know from Ohm's law, Phi is equal to IR. Phi is equal to IR. Therefore, R is equal to Phi by I. Yes. Okay, understood. Now next, as R is equal to Phi by I, we have, now I is fundamental quantity, but Phi is not fundamental quantity. Yes. So we know Phi is equal to what? Work done per unit charge. You know? Yes or not? Phi means what? Potential difference. Phi is what? Potential difference here. So let's move ahead now. And work is equal to force into displacement. Force into displacement. Okay, now can I write like this then? Therefore, R is equal to W by Q divided by I. That is equal to W by QI. Yes. Okay, understood. Then after this, R is equal to W is what? Work done. Work done is equal to what? Force into displacement divided by, this is Q into this I. Now I is equal to what? Q by T, because I is current and this is charge per unit time. So therefore Q is equal to what? I into T. So let's substitute now. So therefore R is equal to, force dimensions already we know, M, one in mass, one in length, minus 2 in time into, S means what? Displacement. So this is length divided by this Q already I told. What is this? IT into this I. So our dimensions will be like this. This M power 1. Yes. M power 1. L and L. How much? L square. This T power 1 and this when it is going up minus 1. So minus 1 minus 2 minus 3. And this I square when it is going up, it will become again minus 2. Yes or not? So 1, 2, minus 3, minus 2. This is what? Your dimensions. Dimensions of resistance. You can keep it in a square bracket. Okay? This is what dimensions of resistance. So how you will read this? Tell me how you will read. 1 in mass, 2 in length, minus 3 in time, and minus 2 in current. Okay? Understood? Clear? Yes? Okay. Let's move ahead. Now, second physical quantity. Yes, this is also very, very important. That is permittivity. Yesterday I have finished. So today let's see magnetic permeability. Okay, so this is also important. Magnetic permeability. Magnetic permeability, and is denoted by mu. Magnetic permeability denoted by mu. Okay, so first, which formula I will use, that is the important thing for this magnetic permeability. We are having one formula, that is F is equal to mu by 4 pi into m1 m2 by d square. m1 m2 by d square. What is that? Formula of magnetic force between two poles of a magnet. M1 and M2 are what? Pole strength. M1 and M2 is what? Pole strength. Right? So first this M1 and M2, M is pole strength. So its dimensions are, just you are getting current into length, that is I into L. Okay. So if you want, you can write even here M1 comma M2 pole strength and having dimensions IL. Mu is permeability, D is distance, F is force. And now what you want? You want this dimensions of this mu. But this 4 pi is constant, so we don't want this. So let's create the formula for mu. So you are getting formula for mu like this. Mu is equal to this 4 pi d square will go here. So F into 4 pi d square. Yes. So F into 4 pi d square total divided by this m1 into m2. Okay, right. Now this one is constant. Which one is constant? This 4 pi is constant. So it don't have any dimensions. Yes. So let's go ahead now. So therefore, mu is equal to F into d square divided by m1 into m. Why? Because 4 pi is constant, and if any constant is there which don't have any unit, then it is dimensionless. So therefore it is dimensionless. Okay, so therefore mu is equal to F d square by m1 into m2, and therefore mu is equal to F dimensions we know, 1 in mass, 1 in length, minus 2 in time. D square means distance, so this is L square divided by m1 and m2 already I told, For M1 it is I into L, and for M2 also it is I into L. Now this L and this L will cancel with this L square. Okay, understood what I did? You can see here this L I have cancelled with this L square. This is also L square, no? So this L square and this L square will get cancelled, right? Now, let's see what you are getting. You are getting like this: mu is equal to 1 in mass. This is 1 in length minus 2 in time, and down is I square. So when it is going up, this will become again minus 2. So the dimensions of this permeability are what? 1 in mass, 1 in length, minus 2 in time, and minus 2 in current. Okay, this is what the dimensions of permeability, right? Next one, next dimensions, let's see magnetic field induction. Okay, what is that? Magnetic field induction, or magnetic induction, or even magnetic field intensity also. So let's see. Magnetic field induction, or just magnetic induction you can write. That is B. Magnetic induction, that is B. Now we have one formula in the 10th class. I think you have learned this. F is equal to I L B, है ना? और force is equal to bill. Bill means what? चूहे का bill, है ना? Yes. So this is what F is equal to ILB, or bill you can write. Bill sin theta actually, but I am not taking sin theta because sin theta is dimensionless. So if you want, you can write here, this is sin theta, but this is dimensionless. I am not taking this because it is dimensionless. Therefore, F is equal to I L B. Okay, now we got one formula which is familiar, or with which we are familiar. So now can I write like this? B is equal to F by IL, F by IL. And therefore now I is current, L is length, F is force. So direct can I write like this now? B is equal to F is what? 1 in mass, 1 in length, minus 2 in time, divided by current is current only. So this is I, and L is length. Again now this length and this length I am cancelling. So what I am getting? B dimensions. See, dimensions of B is equal to 1 in mass. Is there any length term? No, so 0 in length. If any term is missing, you can keep it as a 0. This I, when it is going up, so first I am writing time, and then when this I is going up, then it is going to be power minus 1. And therefore dimensions of magnetic field induction is, or magnetic field induction dimensions are what? 1 in mass, 0 in length, minus 2 in time, minus 1 in current. Okay, is it easy? Very, very easy. Once you understood, it is very, very easy. Okay, next one. One more is there, that is gravitational constant, which is little bit, we can say, lengthy. So let's solve that one also. Okay. So this one, that is gravitational constant. You try to solve maximum. Those which you are not getting or not understanding, you can send me gravitational constant. And it is denoted by capital G. Okay, gravitational constant is denoted by capital G. You know this? Yes. So let's start from Newton's law of gravitation. Newton's law of gravitation. You know this gravitation law. In ninth class only you have finished. So this F is equal, or F is diagonal proportional to M1, M2, and this F is diagonal proportional to square of the distance between the two masses. So if you will write combinedly the formula, you are getting like this: G M1 M2 by D square. So here G is what? Gravitational constant, but it is not the dimensionless constant. It has unit and therefore it is having dimensions also. The physical quantity which are having units, definitely they are having dimensions. Keep it in mind. Except which? Radian and degree. Okay, that is what angle only. Okay, so keep it in mind that also. Next, some exceptions are also there. So let's see. Now I want dimensions of this gravitational constant, that is G. I want these dimensions. So can I rearrange this now? So I am transferring this side. So F D square is equal to G into M1 into M2. And therefore I am getting formula like this: G is equal to F D square divided by M1 into M2. Okay, now F is what? Force. D is what? Distance. So we know force dimensions. So let's substitute now. So this is 1 in mass, 1 in length, minus 2 in time into D square is distance. So distance is L square divided by this M1 is mass only. So this is mass and this is also mass represented by capital M. So let's cancel now this one mass with this. Yes, and take it up. So you are getting formula like this now. G is equal to this M, when it is going up, its power is going to be -1, L3, and this T power -2. Okay, see just what we got. Check it. -1, 3, and -2. So this is what your dimensional analysis for gravitational constant. You can keep it in a bracket. Yes. Okay. So one more dimensions I would like to find, that is specific heat capacity. Okay, let's move ahead and see here one more dimensions, that is specific heat capacity. Specific heat capacity, and I am denoting it with a S, small s, which we have learned in thermodynamics or in thermal properties of matter. Specific heat capacity. Now this formula we know. What is the formula? Q is equal to ms delta theta. This we know formula. Q is what, Ray? Energy. Q is what? Heat energy. So any type, any energy is there, energy is energy. So dimensions of energy are same. So this is dimensions of energy, right? And now I want S. So therefore S is equal to Q by M into delta theta. Okay. Now Q is what? Energy. So Q is energy. So this is nothing but energy. So energy dimensions already we know. Yes. And this delta theta is what? Delta theta is what? Temperature. Yes or not? So therefore, let's substitute now. Dimensions of energy M L square T power minus 2 divided by M is what? Mass. So represented by capital M. And delta theta is temperature. So I am denoting with theta only. Yes. And therefore I am getting dimensions. If we will see for this specific heat capacity, what we are getting dimensions, see. This M and this M will get cancelled. This M will get cancelled with this M. And therefore specific heat capacity dimensions are no mass term present. So therefore 0 in mass. Next is 2 in length, minus 2 in time, and minus 1 in temperature. 2 minus 2 minus 1. And that's why specific heat capacity is not depend on mass, because it is amount of heat required to raise the temperature of unit mass substance by 1 degree Celsius. Yes, already you know this. Okay, so you can keep it in a square bracket. And how you will read? 0 in mass, 2 in length, minus 2 in time, and minus 1 in temperature. Got it? So please solve more and more dimensions. So many of you have not attended yesterday's class. Please go through yesterday's class. Otherwise, you will not understand this. Okay? So let's stop here for today and enjoy the day. Bye.